Hi everyone, welcome to another lecture. The topic today is called the substitution rule, but everybody just calls it U sub. This is what it is. Let's describe it now. We are going to do this both for indefinite integrals like this, when there are no endpoints here, no numbers, as well as definite integrals later. So we are now talking about indefinite integrals again. We've just discussed definite integrals in the last lectures. Let's go back to indefinite so we can describe the U sub rule. So that's what the topic is today. And how do we understand it? We've seen how integrating is the reverse of differentiating. And as it turns out, the U sub is going to be the reverse of the chain rule. So I'm going to have two motivating examples for you here. Here's one of them. We know that the integral of cosine is sine. Sine is a function whose derivative gives you back cosine. Or if you want to be more precise, then you have this plus c as well. But does that also mean the following? I have a question mark here because the answer is going to be no, of course. So a cosine, if you integrate cosine of 4x, does that give you a sine of 4x? Is that going to be the case now? The answer is no. And the way that you check that this is not true is just by remembering what the symbol is supposed to mean. It's supposed to mean a function whose derivative is cosine of 4x. But when you look at sine of 4x, forget about this plus c, that's going to go away with the derivative. When you look at sine of 4x and you take a derivative, because of the chain rule, the derivative of that does not recover cosine of 4x. It's going to give you cosine of 4x times 4. And if you want to find the answer to this integral, you would have to include an extra factor of 1/4 to make it work. So this is true. All right, just once again, think about the chain rule. When you differentiate this part, because of the chain rule, this 4 will come outside and cancel with this 1/4, leaving you with just cosine of 4x. So this is a motivating example. I just have another one. Here's the other one. We know that the integral of 1/x is ln of absolute value of x. Does that mean also the following, though? This is a mistake that a lot of students always make. Doesn't mean the following. If you try to integrate 1 over anything, like cosine square, for example, would that be ln of that thing, cosine square? Maybe inside of an absolute value. Is this true? No, it is not. Once again, how do we check this is not true? Take a derivative of this side. If it were true, then you should recover 1 over cosine square, but that's not going to be the case. When you differentiate this side, you don't recover 1 over cosine square, but rather, what is the derivative? Instead of just 1 over cosine square, which would be the derivative of ln, the chain rule will also force you to multiply that by the derivative of cosine square, which is 2 cosine times minus sine. That's this term here. So the integral itself, this one actually has nothing to do with the ln function. If you think about this, 1 over cosine square is the same thing as secant square. And that integral we know is tangent. That's how you do that integral. Nothing to do with this one, this function. And the integral whose answer is this function, the integral that has this answer, would have been this one. Once again, why? When you differentiate this function, you recover the one that's inside of the integral, the one that's called the integrand function. So the U sub rule is going to be something that allows us to identify situations like this, where you see hidden in here the function 1 over x applied to this particular term, cosine square. And you also recognize the derivative of that term is also present in here. This means that this is the result of a chain rule, and we're going to do the reverse chain rule to obtain this guy. That's the U sub. So stated formally, this is how it goes. Substitution rule, or U sub, for indefinite integrals. Suppose you have functions f and g such that the composite f of g is well defined. You know that composites are not always well defined, they have to be, but we basically never worry about this. If somebody gives you an integral with a composite in it, then that has to be because it was already well defined. So now suppose f is continuous, g is differentiable, and g prime is continuous. Those are all just hypotheses, so we can write the integral. Once again, we don't ever worry about that in calculus. We worry about this formula. This is the U substitution rule, where U is a new variable that depends on the old x via this rule here, U equals g of x. So this rule is saying that whenever you see an integral where you recognize a composite function, and you also recognize the derivative of the inner function in there, then you can define a new variable, u, by using this inner function. And the integral in terms of that new variable is going to be given as with just the outer function and no g, which is a simpler integral that you can now compute. So before we move to examples about how this is applied, let's at least try to justify this formula, this right here. Using what we know about integration, this is something that's supposed to be helpful for consolidating the concepts in your mind. So the function, consider this function, big F of u, represented by this symbol here, the integral of little f of u du. This function, by definition of what this symbol means, it has a u derivative equal to little f. Okay, so df, big F, du is little f of u. That's the definition of this integration in the u variable. So consider this big F function. What is its x derivative? That's a chain rule. If you want to find the derivative of big F with respect to x, according to this way of writing the chain rule, you differentiate with respect to u first, and then the derivative of u with respect to x. Remember that we discussed this particular way of writing the chain rule. And what is that? Well, df du, we just wrote that. That's the little f of u right here. This is a little f right here. And du dx, what is that? Well, the definition of the variable u is right here. It's the function g of x. So I'm going to write that as g prime of x. And finally, I'm going to replace this little u with g of x once again. That's the x derivative of the function big F. That means that you can also represent the function big F by this symbol. Integrate that x function in the variable x. That's going to give you a function whose x derivative is that. So it's, again, the big F. So that's the justification, that this symbol and this symbol, they represent the same thing. All right. So that's the formal justification, but we should probably move on to examples about how to apply this. I'm going to skip this slide for now. Maybe it's better to have done a few examples before going over the process. So here are some integrals that we are trying to calculate. Each one of these has some composite function, and it also includes the derivative of the inner function, multiplying the dx term. So when you look at the first one, what is the procedure going to be? When we look at it, we recognize a composite part, sine x, and then it's raised to cube. And then we recognize that the derivative of the inner function, which is sine, is also there. It's cosine. So we are going to use this inner function as our new u. And every time you introduce a new variable in the integral like this, you also write the following thing. What is the derivative of u with respect to x? That would be cosine x in this case. Now, you split up the differentials. This is just symbolic notation. After taking a derivative, you multiply by dx. That was just a symbol, right? Du dx. It's not like those are numbers, but you can imagine that they are. And this is a symbolic thing that you can write. It tells you how to replace the symbol dx in the original with something that has du in it. Namely, it tells you that cosine x dx can be replaced by du, which is very good because we do have exactly that in here, cosine x dx. So this whole thing here is going to be your du. But then what is the rest of the function? Sine x cubed, that's the same thing as u cubed. U is sine x. So the integral, I'm going to leave this here. The integral sine x cubed cosine x dx becomes the same thing as u cubed du. And that's one that we know how to compute. That's a very easy one. U to the fourth over 4 plus c. A function whose u derivative is equal to u cubed. And now, well, the original function, the original problem was as in terms of x, we have to go back to x. So now that you have the answer in terms of u, go back and replace this u with what it means in terms of x. So sine fourth over 4 plus c. That should be the answer. And it's never a bad idea to check that you have the right answer, just to be safe. How do you check that we have the right answer? Remember, whatever answer you found, take its derivative in x, and it should give you the original function inside of the integral. In this case, you recognize this is chain rule. Hopefully the train of thought here should be very clear to you. How do you differentiate sine to the fourth? That's the same thing as 4 sine to the cube times cosine because of the chain rule. And we also had this extra 1 over 4. So this is sine cube plus times cosine, which checks out. This is exactly the expression that you had in the integral. This is the chain rule. Sorry, not the chain rule, the reverse of that, the u substitution rule. Usually the variable is called u. That's why we usually call it u sub. But of course, you can call it whatever you want. So that's what we're going to do with these other integrals here. Item B, 3 sine of x cubed times x squared. Once again, you look at this and you recognize a composite function, sine of x cubed. And what is also helpful about it is that the derivative of the inner function appears in the integral. You have x squared times 3. That is exactly the derivative of the inner function. So we are going to be calling u this inner function, x cubed. The derivative of u with respect to x is equal to 3x squared. And now you do the symbolic manipulation. Du is 3x squared dx. So in the original integral, when we see a 3x squared dx, we replace that by du. And everything else can be written in terms of a function of u. In this case, sine of u. Maybe I underlined this in red. Okay, so that's sine of u du. Integral of sine, a function whose derivative is sine, that would be the minus cosine function. Because the derivative of cosine is minus sine. So you do need this extra minus in front. And now you replace u back as a function of x. Don't forget that. U is x cubed in this case. Cosine of x cubed plus c. Try to take a derivative of this. Now you should be able to do that in your head and convince yourself that you really get this original function. Item C. Let's do that one here. It fits here. Once again, the composite is sine of t5. But this time we don't actually have the whole derivative of the inner function, t to the 5. That would be 5 t to the 4, right? If you call u equals t to the 5, du dt, in this case, t is playing the same role as x. Du dt is 5t to the 4th. And after you do the manipulation of multiplying by dt, you have du equals 5t to the 4 dt. Well, you don't actually have a 5t to the 4 in the original. You just have what t to the 4. But you can introduce a 5 artificially if you also introduce a 1 over 5. So what you're going to do is this. Put a 1 over 5 which you can put outside if you want, and then a 5. That's introducing extra constant and also getting rid of it. It doesn't change the variable, the integral, but now this can become exactly this term. Sine of 2 to the 5 is the same thing as sine u. This part, 5t4 dt, is du. So this is an integral that you know. Once again, it's minus cosine, but don't forget the 1/5 in front. Plus c. You don't, let me just remark, the constant in front does not need to be like this. Like it was multiplying the whole integral. So now we multiply the whole answer with the plus c. You don't really have to do that. You can always just add the plus c in the end, because that's like distributing the original expression like this, distributing the 1/5 also on the c, and then renaming whatever you got with the name c. Because c is just a constant, if you multiply by 1/5, that is also just a constant. So the plus c can always go in the end like that. That's fine. And it's usually done this way. And the important part is now this, where you want to replace u with g to the 5. This should be the answer. Once again, try to take a derivative and see that you get the original function. So now we can go back to that slide with the general procedure, how to apply the u sub. When you're integrating a composite, look for the derivative of the inner function, the g, or a multiple of it. Like in this case, we did not actually have 5t to the 4th, but we had t to the 4th. So look for that thing multiplying the whole expression. If it is there, then you can apply the u sub rule. I should probably emphasize, u sub is not always going to be possible. It's helpful when it can be applied, but it's not always going to help you. Now, if needed, multiply and divide by the appropriate constant like we just did with the 5, so that you make the exact derivative appear and not just a multiple of it. After you do all that, the inner function becomes your new variable u. The rest, the thing with the g prime dx, becomes symbolically right here. G prime dx becomes your new du, and you integrate with respect to u. But then after you do that, substitute back the u as a function of x. Okay, so this explains everything that we just did here, and now we're going to do some more examples. I have some examples here where they are called functions of a linear function. Anytime where you see in an integral expressions like this, ax plus b, right here, right here, right here, that is always, it's always helpful to have that as your u. We're going to see why. Essentially because du dx is just a number, which you can always introduce in the integral artificially. Okay, so cosine of 2x minus 1. That's a composite function. Let's call u the inner part, 2x minus 1. Du dx is the same thing as 2 in this case. Symbolically, we can write this as du equals 2 dx. So in the original integral, if you see a 2 dx, you can replace that by du. We don't see a 2 dx in there, we just see 1 dx. So we're going to introduce this 2 artificially. The integral is the same as 1/2 cosine of 2x minus 1 times 2 dx. So that's what I mean by introduce artificially. You also introduce the 1/2 to compensate. That's now 1/2 integral cosine of u du. And that's an easy one. Integral of cosine is sine. Here's what I mean. Once again, with the plus c, does not have to be multiplied by the constant if you don't want. And sine of u is sine of 2x minus 1. Now let's mentally take a derivative of this to check. When you differentiate this, you're going to get cosine of 2x minus 1 times 2 because of the chain rule. And this times 2 cancels the 1/2. So it gives you just the cosine that you had in the original integral. This one up here. So it's the correct answer. Let's do this now for the others. 4 over 5x plus 6. This is a composite function. You have, like, maybe the 4 can come outside, first of all. And now this is 1 over something. Once again, a lot of students will immediately try to write ln of that something. That is not going to work. Usually, it's not going to work in this case because of it's going to be off by a constant. That thing inside of the 1 over function should be your u. Du dx is 5, meaning symbolically du is 5 dx. Now we don't see a 5 dx in the integral, but we can if we introduce a 5. So 4 over 5, 1 over 5x, so plus 6, 5 dx. Now just do your substitution. This is 4 over 5, 1 over u du. This integral is ln of absolute value of u, which then becomes ln of absolute value. U was 5x over 6. Not over 6, sorry, plus 6. So that's the final answer. Once again, differentiate this to see that you get the original expression. One last example like this, where you have to introduce a constant. Integral of e to the minus 3y dy. I changed the name of the variable just for fun. That is once again a composite function. You have the outer function e and the inner function is minus 3y. U equals minus 3y. Du dy is minus 3, so du is minus 3 dy. Now we don't see a minus 3, but we can if we introduce a 1 over minus 3, which is the same thing as minus 1/3. So like this, and now you do your substitutions. Minus 1/3 e to the u du. Integral of e to the u is the same thing as e to the u. The derivative of the exponential function is itself. And u is equal to minus 3y. So that's the answer. All right, so these examples were just examples of a linear substitution. In all three of them, the u was some expression of the form ax plus b. Those are always possible to do by u sub, because you can always introduce a constant to make the differential symbol work. The reason is that the way that we introduce this constant is by also dividing by it outside of the integral, like we did here. The problem is if you have to introduce a function, that can be complicated because you cannot multiply by a function outside. A function has to be integrated. So in general examples like this, they have to be very carefully crafted so the u sub actually works. As I said, it's not always going to work. How do we do these integrals now? Let's look at the first one. When you have fractions, if u sub is going to work, then the u is usually in the denominator, because you want the u prime to be multiplying, not dividing, right? So what would happen in item A if we decided that our u is 3x squared minus x? What is du? Du dx is 6x minus 1, so du is just multiply the whole thing by dx. 6x minus 1 dx. Do we see that expression in the original integral? Kinda, it's just multiplied by 2, right? 6x minus 1 times 2 is 12x minus 2. So this is an indication that the u sub rule will work. We are going to write the original integral, which is this, in the following way. Factor a 2 from the numerator. And now 6x minus 1 times dx is the same thing as du. while the whole thing that's in the denominator is the thing that we called u. You see that we did not have to introduce a factor and then also cancel it out. It was already there. This 2 was already part of the original. But we decided to factor it because what's left is the helpful term for the du. And now you're done. Now you just do this integral to ln u, where u was equal to 3x squared minus x. That's the answer to item 8. By the way, if we had changed something about this, for example, if this x squared was x cubed instead, then it would just not work. You don't see the derivative of this denominator in the numerator. It doesn't, it's just not there. And it's not possible to introduce it by multiplying and dividing because it's not just a constant. So u sub would just not work there. Be aware of that. It's not always possible. But yeah, this is basically the only technique of integration that we learn in Calc 1. So it's probably going to be possible in the problems that you see in the homeworks and your tests. Item B, how do we think about B? There's many composite functions that we can see here, but the one that's going to be useful, if you consider this part, sine of exponential, to be composite, the derivative of the exponential is kind of there. It's just missing the factor of 2. So this is the indication of how the u sub is going to work. U equals e to the 2x. So I'm going to copy down the integral here, sine of e to the 2x times e to the 2x dx. If u equals e to the 2x, du dx is 2 times e to the 2x. So you have the expression of du in terms of dx. And as I said, this 2 is missing. You don't see it there, but you can introduce that and also cancel it out by a constant. Because it's just a constant, you can do that. You can make this 1/2 outside of the integral. And now this is sine of, here's when you look at this, anytime that you see an e to the 2x in this expression, you can replace that with u. And we see it 2 times, but we're not going to replace this one with u, because the whole reason why that was there is that this expression is du according to this. So you have to understand where each term comes from, where what is the role for each term in your substitution. This is the one that we're going to replace with u, and this entire expression gets replaced with du. Now, integral of sine is minus cosine. And this u was e to the 2x. That's this integral. Last one. Okay, what do we do here? There's a lot of, the variable of integration is w. There's a lot of square roots of w. If we decided to call u equals square root of w, the derivative of the square root is one that you should have memorized by now. It's 1/2 times the square root. Do we see that also in here? Kind of. It's just missing the factor of 2, but it is here. 1/, square root is right there. This suggests that that's going to be a meaningful substitution. And what is the composite function? In this case, it is secant times tangent. That function, this entire expression is evaluated at the number square root of w, which is going to be the u. So let's see if that works. Secant tangent over square root of w dw. If u is square root of w, du dw, this is the formula that I told you. You can get this by power rule, but you probably memorized it. Du is equal to dw over 2 root w. We have dw over w. in the integral. So we're going to make this over 2 appear by also introducing a 2 in front. So with a 2 here and an over 2 here, which doesn't change the integral, this whole thing becomes up here. This is secant of u, tangent of u. And here, dw over 2 root w is the same thing as du. Now, that's a function that we know how to integrate. Remember that the derivative of secant is secant times tangent. So the antiderivative of secant times tangent is secant plus c. Don't forget the plus c. And replace u with root w once again. That's the answer. Next one, I'm going to solve item A for this one. And B will be just left as an exercise. You should try. Those are two u subs that are going to work for this function. You should get the same answer. So check it using the u sub in item B. It's going to be a little bit more challenging though. So we'll maybe I cover that later in recitation. But you should try first for yourself. Okay, so we have this integral. Calculate it. We're gonna do u equals x plus 1. How do we even know that that potentially is a helpful u substitution? Once again, it's just because this is a linear function. It's a function of the form ax plus b. It never hurts to try u subs using that. They will never give you anything worse. Maybe they don't help, but it's certainly not gonna be bad. So in this case, u equals x plus 1, du dx is 1, meaning du is equal to dx. That's a very simple substitution. Anytime you see dx, you can replace with du. So that's already very good. So the x plus 1 in the denominator is going to get replaced with u. What about the x though? What do we do with that? This is a case where it is necessary for you to find the inverse transformation. You have u in terms of x. In some cases, it is also necessary to have x in terms of u, which is not usually going to be very difficult. Look at this one, just move the 1 to the other side. X is u minus 1. This is the inverse transformation. It means that anywhere where you see an x, you're allowed to replace that with u minus 1. You don't want to do it down here, although you could. You should for down here, you should just think of that is x plus 1. That is exactly what u is. It's the reason why we're calling u that. So this x plus 1 will be just u. But this x up here, we're going to replace with u minus 1. And dx is going to get replaced with du. So what do you get? U minus 1 over root u du. Okay, doesn't look like it helped, but it does help tremendously because now the original expression you could not simplify in any way. It's not like you can, for example, distribute out the square root in each one of the two terms, the x and the 1. That's not how it works. But here you can. You have a numerator that is a linear function divided by the same denominator. You're allowed to split this up this way. Forgot my du. Right, I just split the fraction into the difference of two fractions and then also split the integral. These are the two fractions with a minus sign between. And each one of these is something that you can do by power rule because, well, u over root u is the same thing as root u, which is u to the 1/2. Sorry, there's a minus here. This one is u to the minus 1/2. Each one of these can be done by power rule. Let me just remind you how that works for fractional powers like this where maybe you don't see it right away. What you have to do is add 1 to the power, 1/2 plus 1, and also divide by that same number. In this case, minus 1/2 plus 1. And plus c here, you just need 1 plus c. there's one from here and another one from there, but they get combined. And you can just write 1 plus c. Right, so this is the power rule for integrals. And that's going to become u to the 3 halves. This is also 3 halves, but it's in the denominator, so it's the same thing as multiplying by 2/3. And what about here? This is 1/2. And this is 1/2 in the denominator, which is the same thing as multiply by 2. Finally, just replace u with what it was in terms of x, which was x plus 1. That's the integral. Take a derivative here just to check that you get the original expression, but I'm not going to do that. So this is the u sub in item A. Now you have to try item B as well. I'll leave this as exercise. This step is also going to be necessary. Using this u expression, how do you write x as a function of u? Like you have to square first and then subtract 1. This is how you solve for x in terms of u. You're gonna need this. That's what you're gonna write up here, right? So try it out. One last one before we move to definite integrals. This one is gonna require 2 substitutions. It's just like the chain rule with a composite of 3 functions. We have it right here. One function of another function of another function. Basically, when you look at this, look at the innermost function, the ln. That's a good candidate for your u. What happens if u is ln x? Du dx is 1 over x, so du is dx over x. We know immediately that this is very helpful because we see a dx over x in the original integral. So that's going to get replaced with du. And every ln x gets replaced with u. So the integral just becomes sine of u square cosine of u. And there is no denominator now because dx over x is du. Okay, but now this is yet another one that requires a u sub. Technically a v sub because I'm going to call the variable v, but usually people still call it a u sub anyway. That's a very common name. What is the new variable now in this case? Here is the composite part. V is going to be sine of u, because then dv du is cosine u. So dv is cosine u du. Very helpful because it appears exactly like that in the integral. So the integral is now just v square dv. Now that's one that we know, v cube over 3 plus c. But you have to go back to the original variable, and it goes through u first, right? V is sine u. So this is sine u cube, or sine cube u if you want to write it that way. And then u was ln x. So I just replaced each variable with what it meant originally, all the way back to x. It's really not that difficult to do u sub with more than 2 functions. It's the same procedure, just done twice or more times. I will leave this for recitation. This is going to be something important for later, but I think we should get to the definite integrals. How does substitution work now for definite integrals when you have endpoints? Okay, so now suppose you have functions, once again, little f, little g, such that the composite is well defined. F is continuous, g is differentiable with g prime continues. All of this is just so that the symbol makes sense. Then how does u sub work? It is the same procedure, but you're gonna need to change the endpoints. They're gonna become g of a and g of b, where g is this inner function that defines the variable u. So how do we apply? It's similar to indefinite integrals in the way that you recognize that you need it. It's basically the same. You're still gonna do this procedure of the symbolic change between dx and du. But now you're also gonna need to change the endpoints. after defining the new variable, it's going to work like this. The old endpoints a of b, you think of them as the x values. They're getting replaced with new values, g of a, g of b, which are the corresponding u values. So we'll see examples of this. But after you do all that, here's a very important remark. You don't need to go back to the x variable. There is no x variable later. This, remember, this represents a number. After you do the u sub, if you do it correctly, this is going to be an integral that you know how to calculate. It's going to give you some number like 3/5. That's the answer. You don't go back to x from there. That's how this is different. Few examples. Calculate these integrals. Let's look at item A. So this one is once again one of those where you have a linear function of the form ax plus b right here, x plus 3. That's a good candidate for your u function. U equals x plus 3. You do the same thing that we just did before. Du dx is 1, so du is equal to dx. Now the integral, I'm going to copy it down here, x plus 3 square. Yep. Sorry, the endpoint, yeah, they're good, -1 to 2. How do we change this integral? Well, you're also going to need to know how the endpoints change. So you write things like that. Those are the old endpoints. They are in the variable x. So think of them as being x. When x is -1, what is the corresponding value of u? U is going to be -1 plus 3, which is 2. And similarly, when x is 2, u is 2 plus 3, which is 5. Those are the new values. This is how the change works for the endpoints. Everything else is the same. dx gets replaced with du in this case. And what you have in the denominator is just u squared. But now this is a definite integral. This is something that we discussed in the last lecture. How do we compute this? Remember, the procedure is similar to indefinite. You're going to start by finding a function that is an antiderivative. In this case, the function being integrated is u to the -2. So you're looking for an antiderivative of that, which you do by the, what is that called? The power rule. Power rule for integrals, right? You add 1 to the exponent and divide by that same number. This is an antiderivative, and you evaluate that between the numbers 2 and 5. There's no plus c here. You could have had a plus c inside of this part, but then it goes away when you do the subtraction of the two values. So what is this number going to be? Let me just simplify the function first. That is the same thing as there's a -1, and this is u to the -1. So -1 over u. That is the function that we have between the numbers 2 and 5. What that means is evaluated at 5 minus evaluated at 2. And now this is just a number. It's 1/2 -1 over 5. You see that I don't write plus c here. That's one definite number. There is no plus c in a definite integral. And also you see that we don't ever go back to the x variable. There's no need because we find a number. That number is the answer. That's the answer to item 8. This is the same thing that we're going to do for all these. So b, 0 to pi over 2, cosine squared sine. Pi over 2. Cosine square of x times sine of x dx. When you look at an integral like this, you'll see a composite function and you see the derivative of the inner function. Kind of. The inner function would be cosine. The derivative of that is minus sine. It's not just sine, but it's possible to deal with that by introducing a minus, right? So we are going to call u equals cosine x. which means du dx is minus sine. So du is the same thing as minus sine dx. And the integral itself, we're going to change that by introducing a minus in the sine term and then also another outside. That's still the same integral, but we do that because this minus sine times dx becomes du. But how do the endpoints change? When x is 0, if x is 0, then the corresponding u is, here's u in terms of x, cosine of 0, that is 1. And when x is pi over 2, what is u? Cosine of pi over 2 is 0. You see that the endpoints are going to change like this. 0 becomes 1, pi over 2 becomes 0. It's possible that this happens, by the way. This was an integral in the way that it's usually written, with the smaller endpoint is down and the larger one is up. And now it became something reversed, 1 to 0. That's possible, it happens. And you know how to deal with that, right? You can leave them like that if you want, or you can exchange them by introducing another minus, which will make this one go away. That's up to you. I'm gonna leave them. So we have cosine squared, that is u squared, and everything else was du. Let's calculate this integral. Leave the minus sign outside. U squared, an antiderivative for that is u cubed over 3. That one should get evaluated between 1 and 0 in this order. So leave the minus outside. 0 cubed over 3 minus 1 cubed over 3. That's the meaning of this symbol between parentheses. So, okay, what is the answer here? 0 will be 0, minus minus gives you a plus, and this is 1/3. That's the integral. Last one now. You have from 0 to 1, e to the 2y dy divided by 1 plus e to the 2y. Once again, the variable now is not x, it's y. That is completely irrelevant. When we look at this, we recognize a fraction, first of all. Is it going to be helpful to let u be the whole denominator? In this case, yes. What is the derivative of this denominator? It is something involving e to the 2y, which we see upstairs. So that is a very helpful u substitution. 1 plus e to the 2y. If you do that, du dy is, by chain rule, 2 times e to the 2y. Don't forget the chain rule when you differentiate this. That's where the 2 comes from. So du is 2e to the 2y dy. We almost have that in here. We don't have the factor of 2. So I'm going to write that and cancel it out. Okay, let's change the integral now. Let's deal with the endpoints later. Maybe I'll change the integral first. This whole part will be du. This whole denominator is u. What about the endpoints? If the original variable y equals 0, this one, then your u is, what is u? Here is u. 1 plus e to the 0, that is 2. And when y is 1, if y is 1, u is 1 plus e to the 2. I'm looking here. And that's just a number that we leave like that. Ugly number. So 2, 1 plus e squared. How do we do this definite integral now? Leave the constant outside, 1/2. The function whose derivative is 1 over u, that is ln of u. We don't need the absolute value because these guys are positive. That one has to be calculated between the numbers 2 and 1 plus e squared. So what does that mean? It means ln of the top number minus ln of the bottom number. And that's it. Once again, no plus c, but also no simplification here to be done. Log of a sum doesn't split up in any nice way. There's nothing you can do to simplify this. Very good. One last one, maybe. Compute this. Okay, so what do we think when we look at this? The composite part is right here. We are going to be calling u this inner function, 2x plus 1. And as I told you, whenever you have a linear substitution like this of the form ax plus b, that never hurts. That is a good candidate for u substitution. So du is 2 dx. We don't see a 2 dx, so I'm going to write a 2 and a 1/2. So that's very good. This part, this entire thing is going to be your u. But what about the x? What do we do with this x? This is once again one of those situations where you need to solve for x in terms of u so that you know what to replace it with. In this case, solving for x here gives you this, u minus 1 over 2. That is this x. You can also think it's this x, for example. You can replace this also by u minus 1 over 2. And obviously, you're only going to get u from this entire expression. Right? This is equivalent to this. So it's better for you to just replace 2x plus 1 with u already, instead of replacing this inside x with this expression and then calculating the whole thing. You're just going to get u anyway. Okay, so let's do all of that. Also, the endpoints, if x is 0, u is 1. If x is 1, u is 3. I'm looking here to replace the two endpoints of integration. All right, so the integral becomes 1/2 integral from 1 to 3 x, here's x, times u to the 3 over 5. And then 2 dx is the same as du. What do we do with this integral now? Looks a little complicated still, but this is one of those where it's now possible to distribute terms. Namely, first of all, let's get rid of this 2, leave it outside as 1 over 4. I'm going to distribute u with u to the 3 over 5. So that's the same as u to the 8 over 5. And the other term is minus u to the 3 over 5. All right, now that's just power rule once again. I'm not going to finish this. You should be able to do this. That's now a simple integral. Right, so the reasoning, what happened to simplify this problem, why was u sub helpful in this case? Let's just discuss that. In the original expression, there was no possibility of distributing anything. Raising to 3 over 5, it certainly cannot be distributed over the sum that's inside. That doesn't work. That's not how math works. But the u sub essentially allowed us to call this whole thing inside just one variable. Then the one outside became two variables, became not two variables, but a sum of two separate terms. However, that one outside does not have a power on it. That one can be distributed. And then after distributing, it becomes an integral for which you can compute each term separately, which is how this was helpful. So try to finish this, and you're going to find some number. Okay, this is my last slide now. You know that I like to discuss at least where the ideas come from. We never discussed the justification for u sub in the definite integrals. How do we know that it changes like that? I just want to briefly connect this back to the idea of the Riemann sums. So justification. Suppose that you have an integral, this form of it, the form that happens after the u sub. I'm going to show that this is the same as the form before. So suppose you have this where you also have the change of variable u equals g of x. according to the actual definition of an integral as area as limits of Riemann sums, we know that the value of this integral I here can be found as a limit of Riemann sums of any type, in particular, the one that we call the left Riemann sum, this one. So what we are considering is that we are dividing the interval between g of a and g of b. Imagine that interval, g of a, g of b. We are considering a partition of that into many points that I'm calling ui. And the one that I usually call ui star, the one that I choose inside each one of the pieces, I'm choosing that to be also ui minus 1. That's why this is called the left Riemann sum. So by definition, this Riemann sum approximates this integral, and it becomes better and better the more refined your partition is, with the limit being the exact value. But the u's that subdivide this interval, they all come from an x between a and b, because u is g of x. Remember, u is just a new variable in terms of x. So instead of writing the little u's, we can also write g of little x's. That's all I did to replace the original r expression with this one now. You see, instead of u of I minus 1, I have g of x I minus 1. Similarly here. But, okay, linear approximation, once again, it comes to save the day. What you have here is the same function, g, evaluated at two separate locations which are very close to each other. Those are the xi points, neighboring xi points. You have a difference of g values. Linear approximation tells you that that is approximately g prime at the, let's say, the base value times the difference in x values. So this part, it's not exactly equal, but it's approximately equal. This is linear approximation. Once again, the thing I keep telling you, linear approximation is not just helpful because we can approximate numbers in our heads instead of calculators. It appears in actual math, actual proofs of theorems. So this approximation is approximately this expression. But when you look at this expression finally, what do you recognize? Think about it this other way now. There is one part of it which is a difference of x's, and there is another part of it which is a certain function evaluated at a certain point xi minus 1. The function is this one, f composed with g times g prime. And then you're taking that function evaluated at the points xi minus 1 and then multiplying by differences of x's. What is that? That is a Riemann sum done in the interval of the x's, which is the interval ab, for the function f g x g prime x. So that this Riemann sum here approximates this integral, which is exactly where we wanted to get, right? Remember, I started with the integral that's supposed to be the one after the u sub, and now I got the original integral. So this is an informal argument for why u sub works this way, why it works for definite integrals. And I hope it makes sense in your head, because this really ties together a lot of things, a lot of the stuff that we discussed before, like linear approximation, Riemann sums, and now definite integrals as well. But okay, that should be enough for today. We can do many more examples of Riemann sums in recitation. No, sorry, not Riemann sums, u sub.